Hello, and welcome back to the Cosmic Companion. In this week's episode of Astronomy News with the Cosmic Companion, we talk about Comet SWAN, which could soon grace our skies as the brightest comet in years. We will delve deep into small pockets of water trapped in the crust of Mars, where the salty brine just may be too harsh for life. And finally, we'll learn about the rhythms of the stars and what it can teach us about the nature of these thermonuclear furnaces. And in her first interview since earning her doctorate in astrophysics and astrobiology last week, we talked with Dr. Thea Kozakis, who recently led a study exploring planets around dead stars looking for life. Comets are among the most spectacular sights in the night sky. Those that are bright enough to be seen with the naked eye can be spectacular, and they can hang in the sky for weeks at a time. Sky watchers in the northern hemisphere have not seen a really bright comet since the mid-1990s. Now, a comet discovered by an amateur scientist in Australia is heading toward the sun and is starting to become visible in the early evening sky. The comet may become brighter over the next 2 weeks as it approaches our parent star, and its bright green tail could soon be visible without binoculars or telescopes. However, comets are extremely unpredictable. Just weeks ago, Comet Atlas, expected to put on a spectacular show, shattered as it heated from its close approach to the sun. To see Comet SWAN go outside under dark skies a couple hours after sunset. Take your time and look for a fuzzy green ball or streak low on the northwestern horizon. Bring binoculars if you have them. Now, since the early days of space exploration, mission planners have been careful to practice planetary protection in a quest to prevent life forms from Earth from polluting other worlds. The surface of Mars holds tiny pockets of salty water, and there has been some concern that microbes from Earth could find refuge in these tiny abodes. A new study from the Southwest Research Institute Boulder suggests these watery hideaways may be too salty for life as we know it to exist. Although this may make finding native Martian life less likely, it could also mean that the planet is safer than we believe from biological contamination arriving from Earth. An international team of researchers have studied a class of objects called Delta Scuti stars by studying natural beats created by internal pressures. Using the TESS Space Telescope, astronomers looked at 60 of these stars, attempting to understand how stellar processes unfold in these objects. This study, called astroseismology, revealed many of these stars are younger than astronomers expected to find. This week on Astronomy News with the Cosmic Companion, we have the distinct honor of being joined by the newly minted Dr. Thea Kozakis. She is with the Carl Sagan Institute at Cornell University, and she is an expert on studying the atmospheres of exoplanets, searching for life on other worlds. Welcome to the show, Dr. Kozakis.
Thank you for having me. It's very exciting.
Thank you, and congratulations on getting your doctorate.
Thank you. It's been a long road.
It has. So you recently participated and headed up a study looking at exoplanets around other worlds, specifically those orbiting white dwarf stars. Can you tell us a little bit about that study and what inspired it?
Yeah, so a lot of my thesis was studying how we could find life on planets, Earth-like planets, around dying and dead stars. So a white dwarf is it's a dead star. It's what our sun will become in many billions of years, so nothing for us to worry about. And often when you're thinking about looking for life around different types of stars, usually what you're thinking of is stars like our sun, which are on the main sequence, so it's using hydrogen in its core. Not a lot of work had been done on phases of stellar evolution after the main sequence, so that's mainly what I've been focusing on, because the environment that a planet is in is very important for its atmosphere and its habitability. Because even if we put Earth itself around another type of star and even put it at a distance where it's receiving the same amount of total light as we do here on Earth, the atmosphere is still going to change because the light is going to be different from the star, and particularly things like the amount of UV light is really important because it's energetic enough to break apart molecules and drive the atmospheric chemistry very differently. So what I've been doing as part of my thesis is thinking about how we could find life on a planet orbiting a white dwarf with its different sort of light. And something interesting about white dwarfs is they start off initially very hot, so nearly 100,000 Kelvin. And over time, they don't have an internal heat source. There's no fusion going on. That's why we say the star is dead. It's just cooling down over time. So I was looking for my first paper in the series. I've written a couple of papers on this, was just seeing where in the white dwarf's lifetime could there be a really stable environment for a planet, because you don't want the white dwarf to be cooling so fast that the planetary climate isn't stable. And so I learned a lot about that, and then I was doing simulations to see how the atmospheric chemistry would be different for the planet and what the climate would be like. And in this most recent paper that I've released, what I was doing is I was simulating exactly what we would see if we were looking at one of these planets around a white dwarf. So I was simulating the planetary spectra. So just if we were to observe one of these planets with a next generation telescope, what would these signs of life look like? Because they wouldn't be exactly like Earth's. So I was basically coming up with a sort of guide for anyone when we use these next generation telescopes. What should we be looking for if we're looking at a planet around a white dwarf for life?
Super. And why would you look at essentially, the corpse of a dead star rather than look at a star in the prime of its life like our own sun?
That's a good question. So for one thing, we do like to be able to characterize planets around all different types of stars. And another thing is white dwarfs have really interesting opportunity for looking for life. So usually when we think about looking for life in the atmosphere of another planet, we use the transit method. So we're just waiting for the planet to pass in front of its star, and then part of the starlight will shine through the atmosphere. We could determine the atmospheric composition from there. From there, hopefully, see if there's life. And what's interesting about white dwarfs is they're very small. So it's actually, most of them are only a little larger than Earth. And because of this, if we're waiting for an Earth-sized planet to pass in front of a white dwarf, Earth is going to block a lot of the light from the white dwarf because it's similar size. So if we were looking at a star like our sun and we waited for an Earth-sized planet to pass in front of it, you're going to see the planet's only going to block about 0.01% of the starlight. So a very, very tiny fraction. Whereas for most white dwarfs, if an Earth-sized planet passes in front of it, the white dwarf is so small that the Earth-sized planet would be blocking usually over 50% of the light. So it's a lot easier to make a detection there because nearly any telescope can manage seeing if suddenly half of your light is blocked rather than, something like way less than 1%. So that situation is really unique in terms of looking for life. And That's something we just wanted to look into more, thinking, okay, like this could possibly, when we have these next generation telescopes, we probably wouldn't need as much data to characterize an atmosphere of an exoplanet. So we wanted to think more, what would those atmospheres even look like for an Earth-like planet?
And how would you examine these atmospheres on these distant worlds, and what would you look for if you were searching for life?
So, like I said, we'd have to use a telescope that doesn't exist yet, or rather isn't giving back data yet. So something like the James Webb Space Telescope, so it's often called the successor to Hubble. It's supposed to launch next year, although I'll tell you, it was supposed to launch before I started graduate school, and I took 7 years in graduate school.
I've been following the Webb story for quite a few years now, yeah.
Yeah, so
it's going to be a remarkable instrument once it launches.
Yeah, and it's best that they are. When they delay the launch, we really need James Webb, JWST, to launch when it works, because, you know, Hubble didn't work properly at first when it launched, but it was in low Earth orbit, so you could send people out and maintain it. JWST is going to be quite far from Earth, so if it breaks, we're not going to be able to send anyone to fix it. So I think it's better that we're going to be very, very sure of ourselves before we launch it. So James Webb will have the sensitivity to be able to look into the atmospheres of these Earth-sized planets. It'll be the first telescope that can do that. And also there's things like the extremely large telescopes, the ELTs. So those are ground-based telescopes, and they should have first light in the mid-2020s, hopefully. And there's some observational techniques that perhaps they'll be able to look into the atmospheres of Earth-like planets as well. So it's a really new frontier. I'm sure that when we start to look into the atmospheres of these planets, it'll be similar to when we started looking into the atmospheres of these larger planets we found, where some of it looks sort of familiar, but then there's a whole lot of new stuff that we don't understand. But that's really exciting, because all of the new information we get, even if it confuses us, it's getting us closer to understanding how all these planets work. And although my field right now is a lot of speculation, it's all theory because we don't have any of this data yet. It's going to be really exciting to get some real data, and even if it's nothing like we expect, it's going to lead us to understand terrestrial planetary atmospheres so much better. So we do have to wait a bit now, but soon, hopefully, maybe within the next 10 years.
All right, but get a little bit of, does each new astrophysics doctorate get you designated amount of time on the JWST, or how does that work?
So right now I'm mainly doing all of the theory. So the next 10 years for everyone who thinks about Earth-like planetary atmospheres will be really interesting, because for the first time we'll have the opportunity to not just be pure theorists and modelers. Maybe we can transition into observations. So I haven't done observations in a long time. As an undergraduate, I used to do observations. I did direct imaging of exoplanets around high mass stars, so it was different. So perhaps within the next 10 years, some of us can transition to, okay, let's learn how observations actually work, because it is quite different. Because right now I'm doing these simulations. We understand everything that's happening in the simulation. If there's noise in the simulation, we've put it in there. But in real life, it's a lot messier than that. There'll be issues from the instrument. There's a lot of variability in stars and atmospheres. And especially if we're using a ground-based telescope like the ELT, you have to look through our planet's atmosphere, which is not stable. So hopefully within the next 10 years, I would love to be able to work on some actual observations, but I will need to, of course, catch up and learn more about, okay, what considerations do you have to use with actual data? But luckily, there's a huge community of people already working on exoplanet atmospheres. So around bigger types of planets, though, because those are the ones that we can characterize the atmosphere. Because if you're looking at something like a gas giant, like a Jupiter, there's a lot more atmosphere there. It's basically a huge ball of atmosphere.
Right.
So we'll be able to use techniques that have already been developed for larger planets and find a way to adapt them to smaller planets. So I'm hoping this will bring both like theorists, modelers, and observers together to try to tackle this new problem. In astronomy, we do get very specialized in certain fields, but it's important that we all talk to each other because we all have a different piece to the puzzle.
Mm-hmm.
So I'm hoping within the next 10 years, we'll see more of that.
And finally, what exoplanet or which exosystem has you the most excited?
Oh, that's a good question. So there's a lot of interesting exoplanet systems right now. One that's really interesting, which a lot of astronomers think it's interesting, is the TRAPPIST-1 system. So it's around this star that's much smaller than our sun, so it's called an M star. And it has a bunch of smaller planets around it. It's a more compact system. But because the star is much smaller, the habitable zone where liquid water could potentially exist on the surface of a planet is closer. And there's a few planets that could be in the habitable zone of TRAPPIST-1. So it would be interesting to try to characterize a system like that. I know a lot of modelers have done simulations of trying to figure out how much observing time would we need to look at each of these specific planets. And I think that someone is definitely going to be looking at those planets with JWST because everyone loves the TRAPPIST-1 system because so far from what we found, it is a unique system. It has multiple planets that could be very interesting. And even if we're finding things that aren't anything like Earth, being able to understand the atmosphere of a terrestrial planet outside of our solar system is going to be very interesting for us. Because even in our solar system, we have several small rocky planets, and we already see so much diversity. I mean, Earth is very different than Mars and Venus, and understanding more about these planets is going to be able to help us find life in the universe and potentially another Earth.
That's super. Thank you very much. And once again, congratulations on earning your new doctorate in astrophysics and astrobiology. Congratulations.
Thank you.
On May 26, we'll be joined by Dr. Alejandro Soto of the Southwest Research Institute, who led the recent study on Martian water deposits. We'll discuss his research, talk about water on Mars, and explore how salty conditions there could affect exploration of the red planet. Please stay safe, stay healthy, and keep your wonder alive. If you enjoyed this episode of The Cosmic Companion, please download and share the episode on YouTube or on any major podcast provider. For more details on space and astronomy news, please visit thecosmiccompanion.com or thecosmiccompanion.net.